So good morning, everybody. I got almost 11:10 and welcome. I think we have some high school visitors as well. So good to see you here. It's a beautiful day in Toronto. It's supposed to be a high of 23 Celsius today in Toronto, which is bizarre. And also tomorrow it's going to be +8. So this is the chance to get outside and enjoy yourself. Let me share my PowerPoint and we'll talk about what's going on today. So today, I'm going to go through some problems on the tablet, which solve momentum problems. We've got a team-up quiz to do on Chapter 6. I'm going to get into finishing Chapter 6, so a little bit about jet propulsion. Collisions in 2D, we might talk a little bit more about that on Monday. I'm not sure I'll have time for that. So this is actually from NASA's OSIRIS-REx automated probe, which is out there in space. It's currently 320 million kilometers away from Earth, and it has locked its orbit with an asteroid called Bennu. And Bennu is one of the Apollo asteroids, which means it's an Earth-crossing asteroid. What that means is that these are objects, big rocks in space, which orbit the sun, with the sun at one focus of the ellipse. And it is such that the Apollo asteroids have the property that at perihelion, when they're closest to the sun, they're actually closer to the sun than the Earth. And then aphelion, when they're farthest from the sun, they're farther from the sun than the Earth. And so that means, well, I guess it means it's possible that someday they might collide with the Earth, I guess, because they sometimes are. The exact distance from the sun is here, but they don't do that very often. But anyway, they're pretty easy to access. We got there, and this is actually a little video of an arm which was poked out to try to spray a little bit of nitrogen on the surface of this asteroid and kick up a lot of dust and rocks so that they could collect it. And then they're going to turn that spacecraft around and return it to Earth. It's supposed to come back to Earth in about 3 years from now, and then like send down with a parachute a little box of material which will have some stuff from this asteroid that then we can analyze. Oh dear, forgot about this. We have to do the filter. It's Crazy Friday. Ah! So that means you guys get to choose which of these Snapchatty-like filters I'm going to wear for the whole lecture. Please be kind. Although it's up to you. This is a democracy. I'm not going to influence the vote in any way. Just vote with your heart. Especially if you're an American. Don't forget to vote in the real election, which is coming up. I think it's 11 days away. So. How's the vote doing here? Ooh, interesting. I would not have predicted this one. Okay. I think we have a winner. Anybody else want to click in? This is a little closer than previous polls. All right. And the result is Magicorn. Okay, so it was 40%, and the next runner-up was a sort of a tie between Pirate Hat and Happy Sprout. So let me find my video filter. Where is Magicorn? There it is. Okay, everybody. That's what I'm going to wear for this entire class. Results. Okay, good. And we've got Q&A up, participants up. There's my chat window. Got a lot. Yeah, maybe next week we'll do more of a Halloween thing. Okay. Yeah, this, in case you're a high school student and you're just sitting in, yes, this is an actual university lecture. It's kind of a good question. So right now you're on a call with 535 university students, and this is how we spend our time. It's Crazy Friday, so maybe we start off a little weird. But let's actually do a real physics problem, and then I'll ask for some questions. So this was one that I had planned to do on Wednesday, kind of ran out of time. It's actually the last homework problem on your homework 6 on mastering physics. So if you follow along with this, it could be helpful for you in the actual homework. So I thought it was good to go through it. Usually the last one's kind of the hardest one. You might have found remember that from homework 5. But a record rainstorm produced 304.8 millimeters, which is about 1 foot of rain in 42 minutes. Estimate the average force that the rain exerted on the roof of a house that measures 10 by 16 meters, and assume the terminal speed of the rain to be 10 meters per second. So what this is actually saying is that there is some water hitting the roof, and it may be draining off, but in order to stop the rain, the roof has to exert an upward force. So the idea here is that the rain must stop when it hits the roof. Okay. This requires an upward force from the roof on the rain. And then basically by Newton's third law, the rain exerts an equal magnitude force on the roof. So what I'm going to do is I'm going to define the system in this case to be the rain. And then I'm going to work out what the impulse is on that rain. We've got something to do with the time. So we can divide the impulse by the time to get the force, the average force on the rain. And then at the very end, I'm going to say, yeah, the force of the roof on the rain is equal in magnitude to the force of the rain on the roof to solve the problem. So what we need is we need to, so basically what I'm going to do is say the initial momentum, P initial, plus the impulse is equal to the P final, right? So what's going to happen there is some initial, let's define plus X is down, actually, so that we have P initial is positive, the rain is going down. Then there's going to be some impulse, which will be in the opposite direction, so that the final is 0. The rain stops. The question is, what is the mass of the rain? So the way I did that is, what I'm going to do is assume that the mass density, which I'm going to call rho, is equal to 1,000 kilograms per meter cubed. If you don't have that, you can't solve this problem. So, and also the depth of the rain is equal to 0.3048 meters. So the mass of the rain is equal to the volume of the rain times the density. So it's going to be the depth times the width times the length times rho. So it's going to be the 0.3048 times the 10 meters times the 16 meters times 1,000. I put that all together on my calculator, and I got the mass of the rain is 48768 kilograms. Okay, so that's a lot. That's a lot of, well, I guess that's a lot of rain. It's going over 42 minutes. So basically, if your whole roof filled up with this much rain, this is around 49 tons, metric tons of rain. But presumably in this question, what's happening is that the rain is falling off the roof, going down the eaves troughs or something. But in order just to stop the rain, it requires an upward force of the roof on the rain to give it that impulse. So basically, the next step is to represent mathematically. So what we do is we take the same diagram, the momentum bar diagram, and we translate that into an equation where you've got P initial plus impulse on the system equals P final. And so that looks like this. You've got mass of the rain times V initial of the rain in the x direction, I guess, plus the impulse in the x direction of the roof on the rain, and then you've got the mass of the rain times v of final of the rain in the x direction. This is equal to 0 because it stops. And this is equal to the force in the x direction times delta t. And the initial rain x plus equals 0. You solve this for F. You get F is equal to negative of the mass of the rain times the initial speed of the rain divided by delta t. And so I'm going to convert the rain into SI units to get the F in newtons. So this is important. Newtons is kilograms meters per second squared, right? So if we use minutes for the time, we'll get the wrong answer. So delta t is equal to 42 minutes, but then I'm going to times that by 60 seconds divided by 1 minute. So that you can, the minutes there cancels the minutes there, and you get 42 times 60 is 2520 seconds. So F is equal to negative that big huge mass, 48,768, times the speed of the rain initial, which was the 10 meters per second, it's SI units, divided by 2520 seconds. So these are all SI units, and I got negative 193.5 on my calculator. This is the force of the roof on the rain. Okay, so this would be 193.5 newtons up. The force of rain on the roof is the opposite of that. It's, let's call it 190 newtons to get it into two significant digits down. Average force that the rain exerts on the roof. So hopefully that works for you. Okay. Next on the list. A little poll for you. It's actually look at questions. Let's Naomi, did you have a question?
Hi, can you hear me?
Yes, I can.
Hi, can you explain how you got the mass again, please?
Yeah, sure. That was actually one of the trickiest parts, and it wasn't the obvious thing in this mastering physics problem. So what I did is I said, okay, how much, you know, that's the time is spread out over 42 minutes. So, and the depth of the rain, it says something like produced 304.8 millimeters of rain. What that means is that if you collected a bucket, the bucket would be 304.8 millimeters deep, and that's zero, you divide by 1,000, 0.3048 meters. That's the depth. And then you've got the whole area of the roof of the house, so you've got a volume. And then if you fill that whole volume with rain, which is water, which has 1,000 kilograms per meter, the volume times the density of 1,000 would give you the mass. That's my thought.
Okay, thank you.
Not an easy one. It was pretty hard to do this problem unless you just sort of figured out that's how you needed to do the maths. Fergus?
Yes, hello. I was just wondering, for the sketch and translate section,
Yep.
would we have to put in sketches as well? Like, would we lose marks if we don't? Like, would it be adequate just to write what you wrote, for example?
Yeah, I think that I would get full points for that. Yeah,
And
I guess
also,
sketch, I guess. Like
I was also wondering if you go to the next slide.
we gotta put a raindrop. Yep.
I was wondering why these values would be in the X component if the rain was falling down vertically. Wouldn't it be the Y component then?
Yeah, that's true. Yeah. But I mean, what I did is, like, you can define it. You can call it Z. You can call it W. You can call it anything you want. I defined plus X to be in the down direction, right? It's just a letter.
Okay, so as long as it's consistent, it's fine.
Yeah, I defined X to be down.
Okay, got it. Thank you.
Sure. And then one more from Lilian.
Hi.
Hi.
I also had a question about the mass, because that's the like total mass over 42 minutes if the roof was able to support all of the water without any of it
Yeah.
off of the roof, right?
Yes.
So then the force would be the force required to support, I guess, all of that rain, if none of it came off of the roof. So I was kind of wondering, like, we never have that much rain on a roof since most of it slides off. So it would also not require that much force to hold up the rain that's actually on the roof, right? So how would we be able to find the mass of the rain that actually does stay on the roof, if that kind of makes sense?
Yeah. So that's a great question. I don't know how much rain actually stays on the roof. And it doesn't matter. We're just figuring out what is the average force that's needed to deflect that rain and to stop it from falling at 10 meters per second. 190 newtons is not the force that's needed to support 48,000 kilograms of water. It would actually be 10 times 48,000, so it'd be 480,000 newtons would be what would be required from the roof to hold up that much water, right? You just times by 9.8. So that's much, much greater. This is just the average force, assuming that when the rain hits, there's no gravity force. I haven't included gravity in any of this. I've said that the rain is moving at 10 meters per second. We stop it. How much force does it cause that rain to just not be traveling down anymore? That's an impulse question. So don't get confused with gravity. And yeah, I don't know how much mass, I guess, so that would be an extra force. On top of this 190 newtons, you would also, in addition, need to support how much rain is in the puddles on the roof. So you end up with more than 190 newtons. This is just to stop the rain. Okay, it's a really great question. Good point. Okay. So next thing I want to do, I want to do this pull. So this is, I think Edkina calls this the happy and sad balls comparisons, but you've got two objects. I also did this last time when I talked about dropping a rubber ball of a certain mass versus a damp cloth with the same mass. So you have two objects that have the same mass, and they both are dropped from the same height, so they strike the tabletop at the same speed. The difference is that one's like a damp cloth and one is like a rubber ball. One bounces off the table in scenario one with an equal speed in the opposite direction. And in scenario two, it just sticks there. There's something about the bounciness of the object itself. So I'm going to launch another poll for you to give it a try here. Is it A, the object's change in momentum is larger in scenario one, the object being this ball? B, the object's change in momentum is larger in scenario two. Or C, the object's change in momentum is the same in both these scenarios. And remember, they have the same mass and they have the same velocity just before they impact the tabletop. And then D is that it depends on the time interval for which each object is in contact with the table, that delta T in the collision. This is going to be important when you get to your team quiz tonight, which will be pretty soon. Give you another 10 seconds to click in, please. Okay. Best guesses? Going once, going twice. Just to get 80% voting here. So a lot of you, 62% of you, 285 of you voted for A. That was actually the one that I like as well. Whenever something bounces off a surface, it's not only stopping, it's also reversing its direction. So in this case, so did A. If I define, as I did in the rain question, you guys don't like it when I do this, but if I define plus x equals the down direction, then before what you have is P initial x is greater than 0. And after you have P initial, P final x is like around negative P initial x. And so the delta P in the x direction is the P final x minus P initial x. So it's going to be, minus P initial x minus P initial x is equal to negative 2 P initial x. Whereas here, you've got P initial x greater than 0, the same sort of number, and after P final x equals 0. And so delta P x is going to be just negative P initial x. So this is twice as much. Twice, 2 times as much. Okay? Because that's reverse. Or less. Now, it doesn't always completely reverse. So this is like a approximately equal to. So what we're getting into here is elastic versus inelastic collisions. We're going to learn more about this next week when we get into chapter 7. But I'll tell you right now that the difference between an elastic collision and an inelastic collision is actually how much energy is lost to thermal energy during the collision itself. So chapter 7 is all about energy and kinetic energy and thermal energy and how energy can be transferred back and forth between things. We haven't got there yet. It's not going to be on Tuesday's quiz. But, and the next thing that you're going to have to note, which will come up either in the team up or the next in our demo, is that when you've got a ball which collides with the tabletop is connected to the earth. And the earth has to be considered as part of the system when you're considering momentum conservation in that case. So that's why when these balls, they don't conserve momentum. What they do is they transfer momentum into the earth via the table. So what I want to do next, 11:30, yeah, this is about time, halfway through, for team up time, okay? So today we'll be doing 3 multiple choice questions from chapter, this is one, they're all from chapter 6, okay? As a team of 2 to 4 students in your practicals pod. So this is a time where you have to go and open up Microsoft Teams right now. Your pod team's gonna share the mark. I'm gonna mute here. I'm gonna go over to the help center, Physics 131 Help Center, which I'll give you a link to that next. If you wanna join that, you can, on a different Zoom call is another way you could do it, is I can put you in breakout rooms there. But I don't have enough breakout rooms on this thing to handle it all. Anyway, right now, place a video call. The quiz is called Team Up Quiz Module 3, Chapter 6. It's in Module 3, pretty close to actually where the assessment is. The first step you need to do in your video call is decide who will be the driver. Then you all log into Quarkus and find the quiz. Non-drivers wait. Drivers click Go to Tool, create a group, and then once you get a group ID, let the other people in your video call know the session ID. Non-drivers wait for the session ID. When it comes, click Join Session and type in that ID so that all of you are in the same group quiz together. Once you're all there, then start going through the questions. The driver must wait until everyone achieves consensus. You all kind of vote. If you agree on the answer, click it in and see how many diamonds you get. So you can start now. It is 11:34. So we have until 11:44. If your podmates are not available right now on the Microsoft Teams, you could go to the Physics 131 Help Center with those Zoom coordinates, and I'll let you in there. Hey, everybody. So what I'm going to do is assign to room 1 the 3 of you to room 1, if that's okay. Then Arpit, Evelyn, and Jerry, I'm going to assign you all to room 2. Remember, first thing you need to do is choose a driver. I can, and I think what I want to do is I'm going to wait for a couple more people. Good. So I've got Canran, Sydney, and Timothy. I'd like to assign you to room 3. Erica, hi. I think I just want to wait for a couple more people, see if we can get a room, breakout room, 3 of you. Michael, hi. Okay, good. So Erica, Michael, and Tiffany, I'd like to assign you to room 4. Please go to room 4 and choose a driver.
I was thinking I had blank what to do for the last 3 team module quizzes. Now I got to know what to do.
All you have to do is just wait for, I've got some already here. I'm hoping, oh, Vivian's got it. Vivian, do you have a question? So, Ish.
No, I have a question.
Yeah, what's up?
Okay, I just had a question about the impact, the inelastic collision.
Uh-huh. Let me just get some people into these rooms. 1 second here. So I've assigned Candy, Ishmael, and Kevin, and actually all to room 5. So 4 of you, please go to room 5 and choose a driver and follow the instructions. So Ishmael, you just got to go follow the instructions that are right now on the screen in the other Zoom call. Maybe Victor didn't want to make it 5 there. Sorry, Vivian. I can't do more than one thing at once. I can barely do one thing at once here. You wanted to ask me a physics question, right? Yeah. So what I want to do is Bohan and Wes and Victor wanted to assign all of you to room 6. The first thing you're going to need to do when you get there is choose a driver, and then do the teamwork quiz together. Okay, Vivian. You're not going to participate in the team up quiz? You left Huey and Scott on their own, eh?
No, I just wanted to ask you a question.
Okay.
About the previous wall.
Yeah, the wall. Yep. Yeah. No. So there's an outside force on each ball, which is the force of the table on the ball. In fact, there's also gravity that's acting on the balls. So yeah, the momentum is not constant for the balls. There's an external force. Well, it is a collision, but in this case, you've got an external impulse. You've got J, right? Yeah, exactly. The impulse on the ball that bounces is greater. It's twice as much. That's a good way to do it. Yeah. Okay. Yeah, I think that's going to be true. Yeah, but we're not. That's a chapter 7 concept. So. Lydia. Vivian, have you already done the team up quiz? Do you want to? But your group is driving off without you, I guess, unless they're just all waiting for you. So Lydia, you're a little late, unfortunately. We've got 3 minutes left. I don't really have a group. If 2 more people come in right now, then I can send you to a breakout room with them. I think you might have to just do the team up solo, Lydia. Is that okay? We just create a new group and just go. Yes, nothing new. So what I'm saying is that there's not enough people. You came a little late, but you have all weekend to do the team up quiz. Oh wait, there's Sydney's already done. Okay. So we're going to resume the lecture in about a minute. Remember, this team up quiz will be available all weekend until Sunday at 11:59 if you need to finish it then. Okay. I want to gather people back. Sorry I didn't mute that before. That was must have been a little annoying, but hopefully you just were able to mute me yourself or turn down your volume. I don't know how you could have done that. Yeah, my apologies. So let's go over the questions. Question 1 was saying a very bouncy rubber ball is dropped from a certain height and hits the floor with a downward speed v. Since it is so elastic, the ball bounces back with the same speed v going upward. It's called an elastic collision. Which of the following statements about the bounce are correct? A, the ball had the same momentum just before and just after the bounce. Well, it's kind of true. It had the same magnitude of the momentum. If it said that, but it didn't. So remember, vector, so momentum is a vector. So direction matters. So that's wrong. The magnitude of the ball's momentum was the same, just there we go. That's actually what I'm looking for. And the ball's momentum was constant, so that's not correct. So I think B is right. Makes sense? The direction makes a difference. If you do final minus initially, you have to take into account the direction by using the plus or minus. Florence, definitely the multiple or the midterm assessment 3 will be the exact same format as midterm assessment 1. You answer the questions one by one, and you can't go back and change your answer. First, that's a good zoom tip for me. Question 2: during head-on collision, how does an airbag protect a passenger in the car? So my idea here is that you have some fixed initial velocity that you're at before you crash. And then you also have a fixed velocity after you crash, which is 0. And you have a fixed mass. So in all of these cases, the momentum of the passenger is the same at the beginning, same at the end, and it has to change by some amount. So you need the same impulse on the passenger. So this is not right, okay? So impulse is set by the properties of the crash, how fast you were going and what your mass is of the crash. You slow down, then there'll be less impulse, but that's not what the airbag is designed to do. So that's not right either. It doesn't decrease initial momentum, that'd be slowing down. So this is exactly what it does. It lengthens the stopping time interval for the passenger and therefore decreases the force. Remember that the impulse is equal to the force times delta t. So if delta t goes up, then the force goes down, force magnitude goes down for the same J. Okay, that's the idea there. As shown, 2 people sit at opposite ends of a boat. Hopefully you were able to see this image on the team up. The person to the right throws a large ball to the person on the left. What is the direction of the velocity of the people-boat system at the moment immediately after the ball is thrown? So at that point, they're going to be going to the left. So you've got P total equals 0. So that means if you've got P ball is negative, then P everything else must be the same and positive, right? So that they can cancel each other out and give a total momentum of 0. So it's going to be that's going to, so either going to be that one, A or D. So that rules out B and C. And then once the catcher catches it, the ball becomes at rest again, and so the whole system again goes back to rest. So that's the one that I like is A. These are all internal forces in the system. So the total system is, so it's 0. I know that the whole momentum of the system is 0 because they're initially at rest. Okay, so what I want to do is show you a little demo over here, which is something that if you were actually here in real life, you would be seeing. So what this is called a force sensor. So I can hold it up to you if you want, so you can sort of see it. But it hooks on here. It's called economy force sensor. So when it pushes, it gives this sort of negative force. When it pulls, it gives a positive force. It can give a force up to 50 newtons. So, and what you do is you clamp it onto here, and this measures force, sort of like a scale. And what you do is you plug it in to your data acquisition device. It's called a DAC device, DAQ. The DAC device is hooked up to the computer, and you make a plot. And so what we're going to do is we set a timer so that this is recording a new force measurement every 100th of a second. And then we send the cart along, and it collides. So you'll have zero force, and then you'll have a very large negative force actually during the collision, which is good because what's happening is if we define plus x to be towards the right, then you've got a negative force, right? So that's what's displaying on the computer is the x component of the force. So you can imagine that you came in and did that lab. Share my screen again. And got this kind of data. So what you got here is a situation, you've got a 0.5 kilogram cart on a low friction track, traveling at a plus x direction at plus 1.2 meters per second, say. It collides with the bumper at the end. On the bumper is a force sensor, which you saw, which measures the x component of the force as a function of time. And what you get is that normally the force is 0. But then during the collision, all of a sudden, there's a great big spike in force, which is actually negative. So this is the x component of the force. And if you do find out what all the area is under this, you get that the area is equal to this J sub x is equal to negative 1.1 newtons times seconds. Okay. So the question is, what do you expect to be the final velocity of the cart? So we can do this as an example. If you've got a 0.5 kilogram cart traveling with an initial velocity of, so draw it right here, the mass of the cart is 0.5 kilograms, and the V initial in the x direction is plus 1.2 meters per second. We can define the system is equal to the cart, okay? And then finally, so this is like initial. The initial sketch is that. The final sketch is that maybe the cart bounces off, right? Actually, I don't know if it bounces off or what. It gets some sort of impulse, and you're trying to find VF(x) is question mark. And you've got the J sub x is equal to negative 1.1 newtons times seconds. So, so basically, if you've got P initial plus x, I guess, plus Jx equals P final x, it starts with some positive momentum. It receives a big negative impulse and then ends up with maybe a negative momentum. So, and the way this looks mathematically is the mass of the cart times the V initial x plus the J sub x is equal to the mass of the cart times V final x. And you just solve for V final x is equal to V initial x plus J sub x divided by m mass of the cart. So I got V final x is equal to plus 1.2 meters per second, I guess, minus 1.1 divided by 0.5. So if you keep everything in SI units, I just got negative 1.0 meters per second, which kind of makes sense, right? Okay. Cart bounces and loses some energy. So I'm trying to say some energy. So that's a concept from chapter 7, but if the speed is a little less, it started off with 1.2, it ends up with 1.0, it has a little less kinetic energy. That's probably because there was some heat in the lost in the bumper or something. Do I have time? Yeah. So the other thing I wanted to do, this is saying the impulse of the bumper on the cart, is negative 1.1 Newton seconds. What do you expect will be the final velocity of the cart? Why don't we ask a stupid question here and say the impulse of the cart on the bumper is plus 1.1 newtons times seconds. What do you expect will be the final velocity of the bumper? Okay, so this is coming from Newton's third law. So what we have here, the initial situation, is that the bumper is at rest. Okay, the force sensor or something. Okay, and you've got J sub x equals plus 1.1 newtons. So what is the mass of the bumper? The problem here is that you can't, so what's the system? So define the system. The bumper is connected to the table, the track, which is connected to track's connected to the table. The table's connected to the earth. Okay, so the system is equal to the bumper plus earth. Okay, so the mass of the system is equal to 6 times 10 to the 24 kilograms. That's the idea here. Okay, so there is a momentum. There's an impulse on the bumper, but the bumper is connected to the track. The track is sitting on the table and is connected to the table by friction. The table is connected to the floor, and the floor is part of this whole building. The building's connected to the entire earth. So what you do is you say that P initial plus the impulse is equal to P final in the x direction. So P initial is that it's sitting there. The impulse is that you get some positive value. So you get some positive thing. You get 0 plus 1.1, I guess we'll call that J sub x, is equal to the mass of the system times the V final of the system. Okay, V final of the cart. So V final of the bumper, which is part of the system that's all connected, is equal to J sub x divided by the mass of the system. So it's going to be equal to 1.1 divided by 6 times 10 to the 24 is going to be 1.8 times 10 to the minus 25 meters per second. Okay. So that is why the bumper doesn't move, only the cart moves. It's because it's all connected. So stupid question, but it's good to kind of go over that. I just wanted to finish up. So chapter 7 is not on the midterm next week. It's a good question from Victoria. I am going to be talking about it on Monday and sort of getting going, and the homework will be assigned on Monday, but Tuesday's test is just on chapters 5 and 6. So the cart collision, so the cart itself is on a frictionless track. So it's not connected to the earth. It can move relative to the earth. Whereas the bumper is connected somehow, connected to a wall or something. So that often happens in these problems. You got to see which things are sort of fixed. So the last section of chapter 6 is about jet propulsion. So cars change velocity because of an interaction with the road. Okay, there's a static friction of the road on the tires. A ship's propellers interact with the water. The water pushes forward in the propellers. But a rocket out in space has nothing to push against. So if the rocket and its fuel are at rest before the rocket fires its engines, the total momentum of the system, which is rocket plus the fuel, is 0. And since there's no external impulses, then there's conservation of momentum. So then it burns the fuel, and the fuel is ejected as exhaust backwards at high velocity. So then when you conserve momentum of the whole system, it's like throwing the rocks out of the canoe or something. You propel the rocket forward. So that's exactly how this works. So you define the system as being the fuel plus the rocket. You say V initial is equal to 0. Then you eject the fuel backwards in the negative x direction. So the rocket goes forward in the plus x direction. And the way you set up your momentum bar chart is that everything's 0 initially. You got initial velocity is 0 for the fuel, for the rocket, 0 for the fuel, and there's no external impulse. But then you have internal forces which give a large negative velocity to the fuel and a large, and then result in the same amount of positive momentum which goes to the rocket. This is called thrust. It's the force exerted by the fuel on a rocket during jet propulsion. Typical rocket thrusts measure approximately 1 million newtons, and exhaust speeds are more than 10 times the speed of sound. So this provides the impulse on the rocket that is necessary to change a rocket's momentum. Same principle is at work when you blow up a balloon and release it and it flies through the air, or when you are in a canoe or on a skateboard and you throw a heavy object away from you. So in all those cases, you're conserving momentum. So before class on Monday, I would like you to start in on chapter 7. I will just say that it's not on midterm 3, but it will be on midterm 4. Okay. Remember, Tuesday at 8:10 p.m. Toronto time, there will be a midterm assessment on chapters 5 and 6. There will be 10 multiple choice questions delivered one at a time in 30 minutes. Exact same format as midterm 1, which you guys did just fine on. As usual, I'm going to stick around here until 12:30. There's going to be a TA over in the Physics 131 Help Center, which will be coming on. There's the Zoom meeting ID and the passcode. If I don't see you, have a fantastic weekend, everybody, and happy Friday. And I'm going to turn off the record and then go to the hands.